Imagine a steel that's tough enough for the most extreme jobs you can think of. We're talking aerospace, deep-sea exploration, maybe even inside nuclear reactors. Now, what if I told you we could 3D print it? Well, that's the incredible promise of a new kind of super steel. And today, we're going to dive into the science that's making it all happen.
So, how in the world do you print a material that has these kinds of insane properties? It all comes down to a really revolutionary technique.
When we look at this, we're seeing deep inside the metal itself. This whole thing isn't just about printing a fancy shape. It's about getting to control the material's internal architecture, literally designing how it's built from the inside out to tell it exactly how to behave.
Okay, so the process is called laser powder bed fusion, or L-PBF for short. Basically, a super high-powered laser zaps and melts this really fine metal powder, one incredibly thin layer at a time. It builds a solid object straight from a digital file. It's precise, it's complex, and honestly, it creates some really interesting results right off the bat.
So, what happens when a part comes fresh out of the printer? Well, it's in what they call its as-built condition. And as we're about to see, it has a few quirks that we definitely need to deal with.
The number one challenge here is a property called anisotropy. It's a bit of a mouthful, but all it means is that the material's properties aren't the same in every direction. And as the research points out, this creates a kind of hidden weakness.
The best way to get your head around this is to think about wood grain, right? If you chop a piece of wood with the grain, it splits pretty easily. But try chopping against the grain, and it's way, way harder. It's the exact same idea here. The direction the steel was printed in fundamentally changes how strong it is.
So during the printing process, you can basically orient the part in two main ways. You can build it horizontally, where you're laying down layers side by side like bricks, or you can go vertical, stacking the layers one on top of the other like building a tower. And believe me, this choice makes a huge difference. And you can see just how big that difference is. In its raw, as-built state, the steel that was printed horizontally is a lot stronger than the steel printed vertically. So the big question is, how do we fix this problem and unlock this stuff's true potential?
Well, the answer is a kind of high-tech makeover, a very carefully controlled heat treatment process. This is where the real magic happens.
It's this awesome two-step transformation. First, you hit it with a high-heat reset called solution annealing. Then you follow up with a lower-heat aging process that locks in all the new properties. It's kind of like a blacksmith forging a sword. That specific sequence of heating and cooling totally realigns the steel's internal structure and makes it unbelievably strong. And if you could zoom in to the microscopic level, you'd see something amazing happening. The heat treatment makes these tiny, nano-sized particles, they show up as little white dots, form all throughout the steel. They act like microscopic rebar, locking the whole crystal structure in place and giving it this incredible strength.
And here's the best part. This makeover does two incredible things. It massively boosts the overall strength, and it completely gets rid of that directional weakness we were talking about. After the treatment, the steel is uniformly super strong. It just doesn't matter which way it was printed anymore.
But, as with most things in science and engineering, this incredible new strength comes with a really important trade-off. You just don't get something for nothing. All right, first, the good news. After this heat treatment, the steel's average hardness just skyrockets by nearly 50%. It becomes incredibly resistant to being bent or scratched or dented. But here's that trade-off. Its toughness, and that's its ability to absorb a sudden impact without shattering, it plummets by a staggering 80%. It becomes much, much more brittle. So, the really crucial thing to understand here is this balance. Strength is all about resisting a steady force, while toughness is about resisting a sudden shock. So by making the steel incredibly strong, we also make it more like glass and less like rubber. Choosing the right balance is absolutely everything. For instance, a cutting tool needs crazy strength, but a part on a car needs toughness to absorb impacts without just shattering. So what does this all mean for the future of how we make things? What's the big takeaway from all this? Well, what have we learned? We've seen that the way you print it in the first place is super important, but then heat treatment gives us this incredible tuning knob to fine-tune the final properties. It's this delicate dance between strength and toughness, and getting that balance just right is the whole game. This really drives home the main point. We're not just making parts anymore. We're literally engineering the very fabric of the material itself. This whole line of research really signals a massive shift. The future of manufacturing isn't just about printing objects with cool, complex shapes. It's about printing performance, creating materials with custom-designed properties that we could only dream about before. So it really leaves us with a fascinating question. If you could design a material with any property you wanted, what would you create?